Jnanam paramam dhyayam. Knowledge is supreme.
Okay, now let me state the theorem. This is what we want to prove. So, theorem, this is called Krull's generalize principal ideal theorem. Krull stated it first, Krull stated and proved first for the principal ideals, and then later on for arbitrary ideal. So, but somehow in the literature the same name carries over principal ideal theorem. It's for the ideals in general, but first he stated for principal ideal, but the theorem is really for arbitrary ideal. Okay, so the part 1 is actually this Krull's theorem. So, that is part 1, that if P prime ideal, now as usual A is Noetherian. Is minimal over an ideal A which is generated by R elements A1 to AR, then height of P will be less equal to mu of A, which is less equal to R. Okay, before I go on, I want to first make a few comments. So, first of all, R equal to 1 is what is known as Krull's principal ideal theorem. Okay. Second one, if A is a proper ideal, then height of A, height of this ideal A cannot be more than the minimal number of generators for A. Remember, height of A means minimum of height of P for where P is the minimal over A. Okay. The third one, suppose P is a prime ideal and one says that it has to have height is already, lemma also says height is finite. So, height of P is R, then there exist R elements A1 to AR in P such that P is minimal over ideal generated by A1 to AR. Moreover, height of ideal generated by A1 to AI is I. For each I is equal to 0 to R. You see, note that this 3 is actually the converse of 1. This is the converse of 1. Okay. So, let us prove it. So, note this statement 1 says that minimal prime ideal over a given ideal has height no more than the minimal number of generators for the ideal A. So, if you talk in terms of geometric language, you have this V of A, this is a closed subset in spec of A, and the prime ideals here. So, this is the union of finitely many irreducible components, and irreducible components will be given by the minimal prime ideals. So, this says that the codimension of the irreducible component of this is less equal to R. That is what the geometric content of this theorem is. Okay. So, we want to prove that. So, proof of 1. Okay. So, P is minimal over A, that means there is no prime ideal in between. So, therefore, at localization this is minimal over A localized at P, and therefore, when this is minimal, support of this A mod A localized at P, this support is just a singleton, namely the maximal ideal of AP. Because if there is somebody else, then it will be a prime ideal in between these two, and then PAP will not be minimal over AAP. So, therefore, this means that the ideal in the localization, this is PAP primary. So, in a local ring you have this is a local ring with maximal ideal P, and in that we have a primary ideal, and then our dimension theorem says that we are applying dimension theorem to the local ring A localized at P, and this primary ideal A localized at P. So, the dimension theorem says that the dimension of this ring will be equal to the degree of the Hilbert-Samuel polynomial defined by this primary ideal, and that will be less equal to the minimal number of generators for A. Okay. So, therefore, we know height of P, this is equal to dimension of A localized at P, and this is the dimension theorem here, which says that it is the degree of H A AP, but this degree is less equal to minimal number of generators for the primary ideal, but this number is obviously smaller equal to the minimal number of generators for the ideal in a original ring, because localization will not increase the minimal number of generators, if at all they can go down. Okay. 2 is obvious from A, because say that the height will be achieved by its minimum of the heights of the minimal prime ideals, and height for each minimal prime ideal by 1 is less equal to mu. Therefore, all the heights will be less equal to mu, and therefore, height of the ideal will be less equal. So, clear from definition of height of A and 1. Now, 3. So, proof of 3. 3 is a construction, and this construction will use avoidance, prime avoidance lemma. Okay. So, what do you want to construct? We want to construct a chain. So, we are assuming height of P is R, and from here want to construct R elements A1 to AR in P, such that if P is such that P is minimal over the ideal generated by A1 to AR. And moreover, part is if you take any part of this A1 to AI, the ideal generated by that will have height exactly I. Okay, so that is the problem. We are looking for R elements in a prime ideal of height R, so that P is minimal over the ideal generated by A1 to AR. Okay, this I am going to do it by induction on R, proof by induction on R. R equal to 0, it's clear. R equal to 0, the assertion is clear. Because R equal to 0 means what? Height P is 0. Height P is 0 is it is minimal prime ideal in a ring. So I could take empty set. I could take 0 ideal. So I got a minimal prime over the 0 ideal. So R equal to 1, there is nothing. So assume R is at least 1. And choose, we know height is R, therefore there is definitely a chain of length R which ends at P. So by lemma part 2 in a lemma, there exists a chain like this P0 contained in PR equal to P in spec A. Then first of all note that height of the earlier one PR minus 1 has to be R minus 1. It is bigger equal to is clear because there is a chain of length R minus 1 which ends at PR minus 1. And it can't have more because otherwise I will put that chain before this PR minus 1 and then height of P will increase by more than R. So therefore this is correct. So therefore by induction and hence by induction there exist R minus 1 elements A1 to AR minus 1 in PR minus 1 such that PR minus 1 is minimal over A1 to AR minus 1, and also the property that if I take I of them, the height of ideal generated by A1 to AI is I if I is from 0 to R minus 1. Okay. Now we are looking for one extra guy. If I take this ideal generated by A1 to AR minus 1 and I take its minimal primes. So I take minimal associated primes of A modulo this ideal. Minimal elements in these associated primes, that means they are associated to this ideal and they are minimal. So this is a finite set. This finite set I want to call, I want to give the labels to them. These are some prime ideals from Q1 to Qs. And by 1, what did we prove in 1? If I take any minimal prime over this, the height will not be more than R minus 1. So by 1, height of each one of them, height of Qj will be less equal to R minus 1 for all j from 1 to s. Q's are the minimal primes over the ideal generated by R minus 1 element, therefore height of Qj's will not be more than R minus 1. And height of P, we are assuming height of P is R, this is by assumption. So P cannot be contained in this. in any one of them for all j from 1 to s. Because if p were contained, then height of p which is r, then height of qj will be at least r. But height of qj we know by 1, it is r minus 1, therefore p cannot be contained there, therefore p cannot be contained in the union. So that is prime avoidance, therefore p cannot be contained in union of these q's, which is prime avoidance. So I can choose an element in P which is not in any one of them. So choose that element, I will call it AR which is in P and not in any one of these Q1 union QS. Then I want to prove that that this is the required set A1 to AR minus 1. So what do we want to prove? We want to prove that P is minimal over this and any I A1 to AI ideal generated by that has height I. This is what we want to prove. Okay. So take any minimal prime over this. So first take arbitrary prime ideal P prime which contain this. I want to show that we want to conclude something about the height of P prime. A1 to AR is contained in P prime, therefore I say therefore each Qj will be contained in P prime, because P prime contains A1 to AR minus 1 and therefore it will contain one of the minimal prime for some j 1 to s. Moreover, I want to say that this is proper inclusion, because AR is an element here and AR is not here. That is how we have chosen AR. So therefore this is not equal. So therefore the height of P prime, so therefore height of P prime will be at least one more than the height of Qj. But we have seen the height of Qj is okay. Also I will choose, actually I should have chosen correctly. So in this actually among the minimal primes I will choose not only this, I will choose the one which has exactly height r minus 1, or I may not need it. This is equal to r. Yes, because see it's part of our induction hypothesis that we have chosen A1 to R minus 1, so that this height is also r minus 1. So therefore all minimal primes, there is at least one minimal prime of that which has height r minus 1, and I will only choose, so that is correct what I said, I will choose among these guys the one which has height exactly r minus 1. So these are the minimal primes of A1 to AR minus 1 with height of Qj equal to r minus 1. So for the later, when I chose the AR, so that shows that height of P prime is at least r. On the other hand, okay, so height is r and it contains these r elements. So therefore height of minimal over, so that implies P prime is minimal over A, minimal over A1 to AR if this, then height of P prime is actually R. Actually, why do I need really that? I don't even need this, right? I don't need this. Yes, I don't even need. So, you take all minimal primes in of the ideal A1 to AR minus 1. Yes. Yes, instead of equality, this one here, right? Yes. Okay, that's enough. Okay. So, therefore, what we checked is P is okay. No. This is also, I don't need this also. So, height of P prime. So, what did we prove? We have proved that if I take any P prime which contains A1 to AR, then we proved that P prime has height R bigger equal to R. Okay. So, therefore, I claim now that given P is minimal over A1 to AR. This is what we wanted to prove, right? And height of A1 to AR is R. Okay. So, let us first prove that P is minimal over A1 to AR. If not, then there is a prime ideal in between Q prime. Otherwise, we are in such a situation. It is not minimal, so this is not equal. So, this is a prime ideal Q prime which contain A1 to AR and it is in between. But then these A1 to AR minus 1 are contained in Q prime. So, at least one of the Qj will be contained in Q prime. So, that will imply there exists Qj which is contained in Q prime, contained in P. This is not equal. We have noted that this one has height R minus 1. That was part of the induction, and then this one, then this has height R, we know by definition, by given assumption. So, therefore, it has to be equal here. What do I want to conclude? No, this is not equal here. This is not equal because AR is here and AR minus 1 is AR is not here. We have chosen AR so that AR is not in any minimal prime over A1 to AR minus 1. So, therefore, this cannot be equal. So, this cannot be equal, this cannot be equal. Therefore, but that is a contradiction. So, that checks that P is minimal over A1 to AR. Let me repeat once again. I want to conclude that P is minimal over A1 to AR. So, suppose not, then there will be a prime ideal in between strictly contained in P. But A1 to AR minus 1 are contained therefore in Q prime. Therefore, it has to contain at least one of the minimal prime of A1 to AR minus 1, and that is in our notation, that was Qj. And in that Qj, AR is not there, but AR is in Q prime because Q prime contains this ideal. So, therefore, this cannot be either equal, and we have also checked that Q1 to Qj has height exactly R minus 1. That is because we are using induction. Induction hypothesis says that the ideal generated by part of the A1 to AR, A1 to in particular A1 to AR minus 1 has height exactly R minus 1. That means all minimal primes will have height R minus 1. So, therefore, but this cannot happen because the height of P will increase, then height of P is R given. So, that is not possible. So, that proves that P is minimal over this. Yes, and that proves everything, because then, and also, so the proof is complete. By induction hypothesis, because if I take any part of A1 to AR, the height is I. On the last stage A1 to AR, the height is I, because P is one of the minimal prime, height P is R, therefore minimum, the height of an ideal is a minimum of, so therefore it can't be less. Okay, so it is R. So that completes the proof. Okay, now few corollaries, and also I want to give another proof. See, this proof, I want to give another proof which is not as complicated as this, and also it avoids dimension theorem. So in that sense it will be better, but that I will do it next time, but I want to deduce one corollary at least, or two corollaries. Corollary 1, if I take any A is Noetherian, and if I take any element in A which is a non-unit, and P is any prime ideal minimal over P minimal over this, then height of P is less equal to 1. This is in particular height of a principal ideal is less equal to 1. This was actually Krull's principal ideal theorem. This is the case R equal to 1 from the statement 1. Okay. One more corollary I want to write, corollary 2. Suppose I have a prime ideals P0 contained in not equal to P1 contained in P2 in spec A. So that means what I am assuming, given any, think of it like that, given two prime ideals, one contained in the other, suppose there is at least one prime ideal in between, then I want to conclude they are infinitely many. Then there exist infinitely many prime ideals Q in A such that with P0 contained in not equal to Q contained in not equal to P2. If there is one, then there are infinitely many. This is very astonishing statement, but it is true. Okay, so proof. Okay. So we may assume P0 is 0, and also assume and A is local with maximal ideal P2. This is the usual trick when one wants to concentrate in between the some chain, you go mod the first one and localize at the biggest one, then you, okay. And now let us take, so let A belong to P2. Then there exists definitely a prime ideal Q such that height of Q is less equal to 1. Namely, you can take this A and take its minimal prime ideal over that A. then the height of that Q will be less equal to 1. So, this is true for every A in P2. So, that means P2 is a union over what? Over prime ideals Q in spec A such that height of Q is less equal to 1 and the union of such Q's. Clear? Because you take any element, there is at least one prime of height less equal to 1 which contain that element, and therefore P2 will be union of this. So, if there are finitely many Q's, so now let us look at this set. We are interested in this set Q in spec A such that Q is in between 0 and P2, this, and we want to show this set is not finite. If it was finite, then this will be a finite union, and then by again prime avoidance P2 will be contained in one of them. So, in particular P2 will be equal to that, right, but then that is not possible. When the height of P2 will be less equal to 1, but height of P2 is 2, because there exists at least one prime in between. So, this is, if this set is finite, then P2 will be contained in Q for some Q in this set. Let us call this set as X. But then P2 has to be Q of height less equal to 1. On the other hand, P2 has, but P2, height of P2 is at least 2, since we have P0, we have 0 and P1 here and P2 here, and this we have given not equal. So, height is at least 2. So, that is a contradiction, and therefore, this set is contradiction. So, X is infinite. Okay.